Alrighty, students. Welcome to section 4.4. We're going to look at indeterminate forms and L'Hôpital's rule. These are limit concepts. Now that we're better at derivatives, we can actually look at different limits. And I just want to remind you that limits can always be checked, right? Limits can always. How about we put an L in there? Always be checked. Using a table of values or a graph. Okay. Or you can always check both to make sure you definitely have the correct answer. Okay, please come back to these jokes later, because these jokes will make a lot of sense as we get going here. Well, actually, maybe this one on the right is one we can understand now. So, for example, if you kind of look at this, here you got 0 plus 0, that equals 0. 0 minus 0, that equals 0. 0 times 0, that equals 0. And all these chicks over here, they're all chit-chatting. And then there's this lonely 0 factorial because they are a 1. But now we've got this new guy, 0 divided by 0, and he's like, ruh-roh. I'm not even going to go into it right now. Nobody look at me. All right, you'll get it as we get going. All right, section 4.4, we start looking at indeterminate forms and L'Hôpital's rule. Remember when we found the limit as x approaches 0 of sine of x over x? We could not use the limit laws that we discussed earlier. As we could see, both the numerator sine of x and the denominator x approach 0 as x approaches 0, which gives us 0 over 0, which was undefined. This limit may or may not exist and is called an indeterminate form. I don't know if you remember when we played with these earlier, but we used tables to determine what that limit was. All right, but these indeterminate forms are very prolific. We have a bunch of them. And whenever you get indeterminate forms, you need to do math, smoke, and mirrors in order to simplify them. So the first type of indeterminate form is an indeterminate quotient. For example, 0 over 0 or infinity over infinity. If you have these types of indeterminate quotients, you could go right into L'Hôpital's rule. Before, we used to factor, cancel, multiply by the LCD, multiply by conjugates, do all sorts of math, smoke, and mirrors. Now we're going to use L'Hôpital's. The next type of indeterminate form is an indeterminate product. So for example, if we have 0 times infinity. All right, so if we have 0 times infinity, what we actually need to do is we're going to play a little game. Who's on top? Okay, and basically we pick one of them to stay on top. That one, it becomes 0. And then we put the next one on the bottom. Now, dividing by 1 over infinity is the same as multiplying infinity, okay? Multiplying by infinity is the same as dividing by 1 over infinity. And what happens is, remember, 1 over infinity is 0. So we determine who's on top. We pick the one on top that stays 0. We pick the other one to be 1 over that in the denominator. And we get 0 over 0. And once we have that to 0 over 0, then we can use L'Hôpital's. The next one we're looking at is the indeterminate difference. So the difference is infinity minus infinity. So if I'm going to subtract infinities, I don't know who's bigger, really, and by how much bigger it is. So what I need to do is I need to, build up by the LCD or multiply through by the conjugate to convert this difference to 0 over 0 or infinity over infinity. Then I can use L'Hôpital's. If I have indeterminate powers, and be careful about this one. This one's a little tricky. So for example, if I have 1 to the infinity, that's indeterminate. It's not 1. 1 to the infinity could be 2. Shoot, it could be pi. It could be 100. The other one is 0 to the 0. 0 to the 0 could be many things. Or infinity to the power of 0. All right, for these problems, you're basically going to do log stuff, okay? You're going to use logarithms, and then with that, you're going to convert to 0 over 0 or infinity over infinity, and then you're going to lose L'Hôpital's. Now, is there a procedure to handle any indeterminate form? Yeah. There are a ton of them, and actually, I just talked about them up here. Okay, we're gonna do some stuff and use L'Hôpital's. All right, so let's cover it. L'Hôpital's rule, for just a very, very basic L'Hôpital's rule, just remember you need to have 0 over 0 or infinity over infinity. And for L'Hôpital's rule, let's just suppose you have two functions, f of x and g of x, that are differentiable, and g prime of x is not equal to 0 near the limit point A. So suppose that the limit as x approaches A of f of x equals 0, and the limit as x approaches A of regular g of x equals 0. In this case, we'd get 0 over 0 form. Or let's suppose we have the exact same limits as x approaches A, but f of x and g of x approach infinity. Now, let's say they approach A, but the actual functions approach infinity. So they either both have to approach 0 or both approach infinity. If that's the case, then the limit as x approaches A of f of x divided by g of x is going to be equal to the limit as x approaches A of f prime of x divided by g prime of x. So in other words, we don't have to do math, smoke, and mirrors. If we have the 0 over 0 or the infinity over infinity, we could take the derivative of each without the quotient rule. No quotient rule here. Okay, and then plug in x equals A. Now, again, there is a caveat. We have to make sure that the limit as x approaches A of the first derivative exists, because it might not. All right, it is very important that we check parts 1 and 2 up here of the hypothesis. Okay, so they both have to be differentiable with g prime of x not being equal to 0, and all these limits have to exist and be the same, either both 0 or both infinity. And note that value of A in the limit can be replaced by A from the right, A from the left, negative infinity, or positive infinity. All sorts of options here. Okie dokie, guys. Let's go back to that one we dealt with before. Again, I don't know if you remember, the last time we did this, we used a table. We used a table of values. And let's just go back. Remember when life was simple? And we use tables to evaluate limits. So here's x, and here's sine of x over x. And we use values very close to 0, right? So at 0, we got an error, but plug in values close to 0, like 0.0001, 0.001, 0.01, 0.1, or these negative values, negative 0.0001, negative 0.001, negative 0.01, yada, yada. And we looked at these values, and we use this to actually determine that it's approaching 1. Both of these were approaching 1 as we got close. All right, so this is way back in the day, just a dreamland. Now we're going to use L'Hôpital's. So the first thing we have to do for L'Hôpital's is we have to plug and chug. So let's take a look. What's the sine of 0 over 0? Well, sine of 0 is 0, and 0 is 0. So this means we can use L'Hôpital's. So let's go ahead and do that. Now your notation here, got a little bit of creative freedom. Gotta love that. You can use equal sign with a little parentheses, capital H. I've seen L'H with a little arrow. I'm a huge fan of the L'Hop with an arrow. Or I've seen people just do a capital H with larger equal signs. You can also show the derivative notation if you want to write all that as well. It's up to you. Like I said, a little creative freedom. So I've got this limit as x approaches 0 of the sine of x over x. I know it equals 0 over 0, so I'm going to use L'Hôpital's. All right, the limit goes along for the ride. And now what I'm going to do is I'm going to take the derivative of the sine. So the derivative of the sine is the cosine. Now I'm going to take the derivative of x. Well, the derivative of x is 1. Now I plug and chug. So I've done L'Hôpital's, and now I plug it in again. So cosine of 0 is going to give me, good, 1. And this 1 goes along for the ride. And then 1 divided by 1 is 1. So the limit as x approaches 0 of sine of x over x is going to give me plain Jane 1. Now let's find a few more limits. So again, remember, plug and chug. Okay? If you get 0 over 0 or infinity over infinity, I should put this as a number 2, then you do L'Hôpital's. L'Hôpital's, La Hospitals. I don't know. I really would like a French person to tell me how it's pronounced. Or someone who speaks French very well. And then next, you just repeat. Okay, sometimes you have to do L'Hôpital's a few times. Plug and chug, make sure it still fits the rules of 0 over 0 or infinity over infinity, and then repeat. And you do it, but nobody can become 0. All right, so first thing I'm going to do is I'm going to plug in 0. So here I have sine of 0, not sine of theta, sine of 0 minus 0 all over 0 cubed. And that gives me 0 over 0. So I'm going to use L'Hôpital's. So the limit as x approaches 0, I take the derivative of the top. So I'm going to have the cosine of x and then minus the derivative of x is 1. And then the derivative of x cubed is 3x squared. Now remember, L'Hôpital does not require us to use the quotient rule. We just take derivative of the top, derivative of the bottom, because we're finding the limit. We're not evaluating the derivative of a quotient. Okie dokie. Plug and chug again. So now I've got the cosine of 0 minus 1 all over 3 times 0 squared, which still gives me 0 over 0. So I'm going to do L'Hôpital again. So I've got the limit as x approaches 0. I take the derivative of the cosine of x minus 1. The derivative of the cosine of x is the negative sine of x. Derivative of negative 1 is 0, so I don't have to write it. The derivative of 3x squared is going to be 6x. Time for plugging and chugging again. So I'm going to have negative sine of 0 all over 6 times 0, which gives me 0 over 0, which means I can use L'Hôpital again. So the derivative of the negative sine of x is going to be the negative cosine of x. And then the derivative of 6x is just 6. And now I can plug in my 0 again. So I'm going to have negative 1 over 6. And mind you, my plug and chug finally yielded a result, so that's my answer. Remember, always check final answers. This one wasn't too bad, as you know. They always get worse, right? Okay, so always check your final answers. Make sure you know that your work is matching. Taking a look at this one. Okie dokie. So if I plug and chug, I've got e to the infinity all over infinity to the power of 3. E to the power of infinity is infinity. Infinity cubed is also infinity. So this means I can use L'Hôpital. So the limit as x approaches infinity, I'm going to take the derivative of the top. So the derivative of e to the x is e to the x. And then I'm going to take the derivative of x cubed. So I'm going to get 3x squared. And I'm going to plug and chug again. So e to the infinity over 3 times infinity squared. And that's going to give me infinity over infinity. So that means I can use L'Hôpital's rule. So I'm going to take the derivative of this one. So the derivative of e to the x is e to the x. The derivative of 3x squared is going to give me 6x. And if I plug and chug, I'm once again going to end up with infinity over infinity, which means I can do L'Hôpital again. So the derivative of e to the x is e to the x. See a pattern here. And the derivative of 6x is just going to give me 6. Now plug and chug. Now I have e to the infinity divided by 6. Well, let's think about that. If I have infinitely many cookies, and 6 students I wanted to divide those cookies up between, how many cookies do the students get? Yeah, they get infinity. Infinity divided by 6 is still infinity. So the original limit, as x approaches infinity, of e to the x divided by x cubed is infinity. All right, let's look at the next form. So this is a product form of 0 times infinity. And remember, this is the one where we play who's on top, okay? We choose one of them to be on top, and we then turn it into 0 over 0. And we get that 0 over 0 by doing 0, oh, not that, by doing 0 over 1 over infinity. Or we get it to be into infinity over infinity, and we do that by doing 1 over 0 over infinity. So let's take a look. This one involves the limit as x approaches pi over 2 from the left of tangent. So let's take a look just at the graph of the tangent function and get an idea of what we've got going on here. So here's negative pi over 2, here's pi over 2, here's the tangent function, and then same thing over here. Okay. So if I were to plug this in, so I've got pi divided by 2 minus x. This right here, this would give me 0. And then the tangent of x, if I look at that as that approaches pi over 2 from the left, okay, that's going to give me infinity. So now I need to figure out who should be on top. Now, let's keep in mind, I want things to cancel. So here's one of my pieces. Here's the other of my pieces. So I'm going to pick who's on top. No. So I'm going to put pi over 2 minus x on the top, and I'm going to put 1 over tangent of x in the denominator. And the reason why I'm going to put the 1 over tangent of x in the denominator is because we know what the 1 over tangent of x is. Yeah, it's the cotangent of x. And that's something that we can easily take the derivative of. So let's plug in our pi over 2 to verify that things are working out, that it's going to be in the correct form, either 0 over 0 or infinity over infinity. So I'm going to plug in pi over 2 minus pi over 2 on the top, gives me 0. And then the cotangent of pi over 2 also gives me 0. So that's what I want. So now I can use L'Hôpital's. So this is a limit as x approaches pi over 2 from the left. I'm going to take the derivative of the top, which is going to be 0 minus 1. And then in the denominator, I'm going to have negative cosecant squared of x. Now before I plug anything in, I'm going to clean house. And when I am dividing by the negative cosecant squared, remember that that's the reciprocal of the sine squared. Then also, these negatives are going to cancel each other. So when I'm dividing by a fraction, I multiply by the reciprocal, and 1 divided by the sine squared of x just is the sine squared of x. So when I plug in pi over 2, I'm going to get 1 squared, which is 1. Okay, for this problem here, it helps to know what the natural log graph looks like and what the sine graph looks like. Okay. So here, sine of x is going to be 0, and natural log of x is going to be times negative infinity here. So this one will work. Sorry, my dog is barking. So again, we need to play another game of who's on top. All right. Now, I'll tell you a little secret. Oftentimes, you do not want the natural log on top, but you never know. Right? Isn't that how math goes? Sometimes you try something and it works. Other times you try something and it doesn't work. So if I were to put the natural log on top, it would look like this. And I would have the 1 over the sine of x. Or if I were to put the sine of x on top, I would have the natural log of x in the bottom like this. Now again, like I said, oftentimes you don't want this. You want the natural log on the top. But I'm going to tell you, this one is icky. You can do L'Hôpital's a bunch of time and you get into a L'Hôpital death spiral. However, this one only takes a couple steps. So let's look at it. Let's evaluate it first to make sure it works. And actually we get 0 divided by 1 over negative infinity, which is 0 over 0. And so that means that we can use L'Hôpital's. Okay, we can use L'Hôpital's. So let's do that. The limit as x approaches 0 plus. Now, one thing I'm going to do is I'm going to write this as the natural log of x to the negative 1, so I could take the derivative a little bit better. So here I've got cosine of x. And then when I take the derivative of the denominator, my negative 1 is going to come down. Natural log of x stays the same. This turns into negative 2. And then I'm going to take the derivative of the natural log of x, which gives me 1 over x. So now, let's look at this. Let's do some house cleaning before we do plugging and chugging. So I've got a negative 1 here. I'm just going to stick it up there. And I'm going to have 1 over the natural log of x, and this is squared, times 1 over x. All right, now let's plug in that 0. So if I plug in 0 to the top, I get negative 1. If I plug 0 into the bottom, I'm going to get 1 over infinity squared times 1 over 0. I was going to write infinity again, but 1 over 0, if you look at 1 over x, that's going to give you infinity. So this really gives you 1 over infinity, which is going to give you 0. Interesting, eh? I should just skip example 4. Fuck that problem. Oh, I accidentally skipped example 4. So just go ahead and move on to the next section. Okay, for the indeterminate form of differences, we're going to have infinity minus infinity. We're again going to try to rewrite the expression as 0 over 0 or infinity over infinity by using a common denominator and or rationalization. So if I look at this problem here, I'm going to have infinity minus infinity, and that doesn't work. So we need to rewrite it. Now, if I'm going to try to get an LCD, the best way for me to get an LCD is to write everything, especially since I've got trig functions here, write it in terms of sine or cosine. So I'm going to have the cosecant is the sine of x, and the cotangent is the cosine over sine of x. And then these are already over the sine of x, and so I'm going to have 1 minus the cosine of x all over the sine of x. Now if I plug this in, I end up with a 0 over 0, and that's fantastic. That means I can use L'Hôpital's. So the limit as x approaches 0 of the numerator is going to be a positive sine of x, as I get 0 and then a negative negative sine of x. And the derivative of sine of x is a cosine. Then when I clean house, I get the limit as x approaches 0 of the tangent of x. Now if I plug in 0, I end up with 0. So all of this gives me a limit of 0. Let's try another one. Notice again, I end up with infinity minus infinity. So for this one, we're going to multiply by the conjugate. So I've got the square root of x squared plus x minus x, and I'm going to multiply that by the conjugate of x squared plus x, the square root of plus x, and then divided by plus x. Next, let's go ahead and FOIL out and cancel some things. The denominator is going to stay super unfancy. It's just going to be the square root of x squared plus x. On the top, we're going to have x squared plus x minus x squared. Because we have a difference of squares, right? The insides pop out. Just so you know, the first thing squared minus the second thing squared. Then, sorry for that lip smack. Then, notice our x squareds cancel. And if I plug this in, I'm going to end up with infinity over infinity. So I can use L'Hôpital's. So, limit as x approaches infinity. The derivative of x is 1. The derivative of the denominator, I'm going to bring the 1/2 down. And then multiply by the derivative of the inside, and then plus 1. All right, now that's a little icky, and we really don't want to plug in anything until we simplify it. So let's do that. So over here, I'm going to have 2x plus 1. Here I've got this plus 1. All over 2 square root of x squared plus x. All right, at this point, I'm going to go ahead and use some old school tricks. Now, keep in mind, kind of pause and pull this out here. So let's say I've got the limit as x approaches infinity of just this thing. Okay, because everything else is 1, this is the thing that I need to look at. This one, if I were to plug it in right now, I'd get the infinity over infinity, but I'd also get some really, interesting derivatives. But if I were to look at the old tricks of multiplying by the effective degree of the denominator, I'm going to multiply both of these by 1 over x. So the limit as x approaches infinity. Then I'm going to have 2 plus 1 over x. And on the inside of this, I'm going to have 1 plus 1 over x. Because remember that x is equal to the square root of x squared when it goes inside. Now if I plug in the infinity, I end up with 2 plus 0 divided by 2 times the square root of 1 plus 0, which is going to give me 2 over 2, which is 1. So then if I look at this, I end up with 1 divided by 1 plus 1, which is going to give me 1/2. Neat, huh? All right, indeterminate forms that have powers, we need to use logarithms. Okay, so the indeterminate forms of 1 to the infinity, 0 to the 0, infinity to the 0, you need to try taking the logarithm of both sides. And remember that we use this formula, LOP, oh my goodness. So the log, base b of a to the power of p, that p comes down, okay? All right, so the first thing I'm going to do is I'm going to let y equal this limit. Now what I'm going to do is I'm going to take the natural log of both sides. You know, a couple things are going to happen. This limit, I'm going to move outside of the natural log. But I'm also going to take this power and move it outside of there. So we're going to get the natural log of y is going to be equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Now if I plug that in, I get the infinity times 0 form. So I need to play a little game, as we know, of who's on top. And just remember, as we get going here, this thing is equal to natural log of y. So when we find this value, what we're going to do is we're going to say the natural log of y equals something, and then that means that y is equal e to that something. So whatever it is that we get here, we're going to have to plug that back in. All right, so let's go. We're going to play who's on top. So the limit as x approaches infinity of, let's leave the x on the top, and then let's try the natural log of 1 plus 1 over x on the bottom. Except for I didn't write it under 1. My bad. Oh, can I squeeze it in there? Natural log of 1 plus 1 over x. Oh, so tight. All right. Let's do the other one who's on top. So the limit x approaches infinity, and we'll leave the natural log of 1 plus 1 over x on the top, and then we'll have 1 over x in the denominator. All right, I don't know if you remember. Did I say this? I can't remember. I don't know if you remember. I don't know if I remember. Oftentimes you don't want to have that natural log in the denominator spot because you then have to use like some really icky chain rule. We still have to use chain rule, but just so you know, we're going to try something like this. It looks a little intense, but that's what we're going to give a shot. So we're going to do the limit as x approaches infinity. And if we plug this in, we do end up with the 0 over 0 form. So we're going to do L'Hôpital's as we go up here. And I'm going to end up with, so in the denominator, I'm going to have a negative 1 over x squared. In the numerator, I'm going to have 1 over 1 plus x times the derivative of the inside, which is a negative 1 over x squared. And look at this wonderful thing that happens, is that these guys, poof, poof, cancel. And now what I end up with is the limit as x approaches infinity of 1 over 1 plus x, 1 over x. And how exciting is that? Because that's 1 over 1 plus 1 over infinity, which is like saying 1 over 1 plus 0, which is 1. Da, 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 da. All right, but remember, this is natural log of y equals 1. So that means that y equals e to the 1, which is e. Okay, so don't forget that part. So then we just put it together. So the original limit which we had set equal to y, is equal to e to the 1. Nice, huh? All right, for this one here, you plug this in, we end up seeing it's a 0 to the 0 form, which is the indeterminate. So we're going to do the same thing. We're going to let y equal to this limit. Then we're going to take the natural log of both sides. Sorry for the nasty handwriting. It's getting dark and I have a glare. So to move the limit outside of the natural log, and we're going to move the x in front of the natural log. Because remember, those are the legal things to do, okay? This one moves outside of this, and then this power means it can move outside of this as well. All right, when I plug this in, I see that I'm going to get a 0 times infinity form. So I need to play again who's on top. Remember, we don't really want the natural log on the bottom. So what we're going to do is put the natural log of sine x on the top, and then 1 over x in the bottom. And now let's plug it in. If I do that, I see I get it into infinity over infinity form. So that means I can use L'Hôpital's. So let's do that. So I'm going to have sine over cosine. And then here I'm going to have negative 1 over x squared. Now, if I simplify this, I'm going to end up with a negative x squared times the cotangent of x. And if I plug that in, I end up with 0 times infinity, which is bad, so then I'm actually not going to write this. And I would say, how else can I write the cotangent? Well, I can write it as the tangent. And if I do that, I get 0 over 0 again, and I think, yay, and I do L'Hôpital's. And then I'm going to get negative 2x all over secant squared of x. And this gives me negative 0 over 1, which is 0. All right. But remember that the natural log of y is 0. And y, which is our limit statement, is equal to e to the 0, and e to the 0 is 1. So therefore, the limit as x approaches 0 from the right of sine of x to the power of x is equal to 1.